Okay, so with our first subset of presentations with this unit, we were talking about precipitation reactions, net ionic equations, and then also with our just last one, talking about some gases and how those can form in reactions. And now we're going to be talking about the next reaction type on our list, which is acid-base reactions. This is going to be an introduction. You'll get a lot more acids and bases as we progress in the course, that is. But this is going to be a good introduction to some acid-base stuff. We're going to start off kind of simple with some things that you should have learned from General Chem, and I'll try to speed through those, and then we'll get into some parts that get a little bit more dicey. They get a little bit more math-heavy as we do some different mathematical calculations using acid-base reactions and acid-base ideas. So here we go. All right, so general properties of acids and bases. This is all stuff that you should have learned in general chemistry. How they taste, how it feels, what actually makes it up, and some common examples, and the fact that they turn chemical indicators different colors. So just take a moment, read through this list. If there's anything that shocks you or whatever, write it down. We'll talk about it, but pause if you need to for a second here. Okay, moving on. We did, at least in my class, I'm fairly certain that Mr. Wolf would also discuss this. We talked about a couple of different acid-base definitions. And the first one that we discussed is actually the oldest, the first to come about, which is the Arrhenius definition of acids and bases. Arrhenius basically described acids and bases as we do in the most generic way, that acids have hydrogen ions, that bases have hydroxide ions. And so hydrochloric acid and sodium hydroxide are perfect examples of acids and bases under the Arrhenius definition. However, it doesn't perfectly categorize everything. The biggest problem was ammonia. The base definition here is quite limited. In fact, ammonia is a base, but based on the Arrhenius definition, we have nothing to understand that based on. So because Arrhenius's definition was limited, a couple other guys came along and they determined a more inclusive definition, which is the Bronsted-Lowry definition. That funny O in Bronsted, I do believe that gentleman was Swedish, and so that's a Swedish letter O thingy. Bronsted and Lowry were actually working separately, but they published at nearly the exact same time. So even though they weren't working together, both of their names are actually attributed to this definition. So the Bronsted-Lowry definition is all based on protein transfer. Did I say protein? Proton transfer. So the acid is the species that will donate the proton. Again, a proton is an H plus ion. They are synonyms. So if you have an H plus, it means you can donate it. You're an acid. If you're a base, well, you didn't start with an H plus, which means you could accept it if the acid decided to give it to you. So acid-base reactions, they happen all the time together. An acid and a base react. The acid donates, the base accepts. This fully explains why ammonia is a base, because if you take a look at this equation here with ammonia reacting with water, you can see that there is a transfer of a proton. Do you see it? Do you see where the proton came from and where the proton went? And if you see that, can then you explain which one is an acid and which one's a base? Okay, so if not, or if you're just continuing to watch the video, take a look. Do you see that the H2O, that one of those H's has to be transferred over to the NH3, which is how it becomes NH4, which is how the H2O becomes just OH. So the H2O donates the H+, meaning it's the acid, and the H3, or ammonia, will accept the H+, and that makes it a base. Voila. So the Bronsted and Lowry definition, again, is just much more inclusive, and it isn't that limited version that Arrhenius came up with. Okay, so next thing. We have to understand that acids and bases are not created equal. That some acids and bases are considered strong, and some acids and bases are considered weak. And it might be something you can even think of. Like, for instance, you would probably not consider drinking hydrochloric acid. You probably would not consider drinking battery acid, which is sulfuric acid. Nitric acid, equally as bad. But citrus juices like orange juice and lemon juice and lime juice, would you eat those? Of course you would, because you're any normal human being. So already, like, you recognize that not all acids are created equal. So the strong ones, what it means to be strong means that if you put it in water, it's going to completely ionize, meaning it's going to completely and 100% separate into ions. It's also considered to be a strong electrolyte. When you think about electrolytes, it basically means that you've got ions in solution that have dissolved. That's really all it means. What you have to understand about these is that when you have strong acids, they always get written as ions in net ionic equations, and that's because they completely ionize. So if you're dealing with something like hydrochloric acid or sulfuric acid or nitric acid, you always, always, always break it into ions. However, if you're a weak acid, it's completely different. In fact, weak acids, and this is the reason why they're weak, is that they only partially break down. So things like vinegar or, again, lemon juice, when you put them in water, some of that acid stays together as the full compound, and some of it will partially, some of it will ionize. So again, partial ionization. These are considered weak electrolytes because they do not produce as many ions in solution. And this is the really important part, okay? Most important thing that I've told you in a little while here. Weak acids and bases have to be written as a molecular compound in net ionic equations, meaning you do not break them into ions, even if it's aqueous. That's because it's a weak acid. And based on what we know chemically about weak acids and how they react in water, they mostly stay together as the molecular compound. So this is going to be a really important tweak to what we've already learned about net ionic equations, and that will come up in your homework. So FYI, crazy important, the very last purple bullet point, you have to understand that if you produce something like acetic acid, which is HC2H3O2, that stays together as a molecular compound, it will not be broken into the hydrogen and the acetate ion, okay? So extremely important. All right, so you may be asking yourself, well, Mrs. Seagrave, what in the world is strong and what in the world is weak? So this is something you need to make a note card of. Strong acids are any of the acids in the list that you see on the left side, and strong bases are any of the ones that you see on the right side, meaning that if you produce in a chemical reaction, or if you deal with these in a chemical reaction in any way, shape, or form as reactants or products, they always get broken into ions. I'll get back to that in a second. If it's another acid or another base, it's weak, okay? So if it's not on this list, you cannot break it into ions in equations. If it is on the list, you must break it into ions, okay? Hopefully that's clear. The thing with the pink ones, calcium hydroxide, strontium hydroxide, and barium hydroxide, if you take a look at your solubility chart, you might notice that they have little asterisks beside them, which means that they have limited solubility, yet they are considered strong bases. So this is sort of that weirdness where they have sometimes they're insoluble and will form precipitates, yet at the same time they're considered strong bases, so you're supposed to break them down. It's a gray area. So just keep that in mind, gray area. If you have questions about that or want clarification, please ask. But in the meantime, you need to make a note card of this information. Pause the video now, please. Okay, continuing on. Oh, look at that spin. Continuing on, neutralization reactions. A neutralization reaction is basically an acid-base reaction. It's when you take an acid and a base, you react them, and you form usually water and an ionic compound, which is also known as a salt. Not literally salt, NaCl, but just a salt. It's a more generic term. So try this. Write the molecular and net ionic equation for the neutralization of hydrocyanic acid with lithium hydroxide. Pause the video, see what you can do with it. How many of you are like, what the heck is hydrocyanic acid? Yeah, raise your hand. Yep, I see all your hands. Okay. Hydrocyanic acid. So cyanic. Okay, well, that's cyanide. That's Cn negative. And the fact that you then have the acid part means you just have to add a hydrogen. So it's actually just HCN. Lithium hydroxide, hopefully you came up with, is LiOH. And at that point, so if you know it's HCN plus LiOH, now can you continue? Okay, so here's our reactants. This is basically a double displacement reaction. So there are my products. And what you now need to recognize before you go any further to write a net ionic equation is that HCN, hydrocyanic acid, that was not on your list of strong acids, meaning it's a weak acid. Lithium hydroxide was on the strong base list, so it's a strong base. What the heck's that mean? Well, strong acids and bases get written as ions, and weak acids and bases stay together. So, if we follow that lead, do you understand why HCN stays together and why LiOH breaks down? Do you also understand that lithium cyanide contains lithium ion, which is a group 1A metal cation, and those are always soluble all the time. And then again, water is just water, liquid water, so you don't break that down into anything. So this would be your complete ionic equation. You have a lithium spectator ion, and so your final net ionic equation is hydrocyanic acid reacts with hydroxide, producing cyanide ions and liquid water. Okay, so you got to now start watching out for these weak acids or weak bases that are going to pop up and cause you some problems. So that's why you made the note card. Just have it handy, okay? All right, so next. What do you notice about the net ionic equation for the neutralization of a strong acid by a strong base? Well, what I mean is something like this. So this is a strong acid, hydrochloric acid, and this is sodium hydroxide, a strong base. Notice I produce sodium chloride and I produce HOH or H2O, which is water. Okay, so notice anything yet? Probably not. Okay, let's keep going. So this is a molecular equation. Let's write the net ionic equation. So take a second, pause the video, write the net ionic equation. Okay, so hopefully you came up with this as your complete ionic equation, and then you recognized your spectators of the sodium and the chloride ions, and you came up with this as your final answer. What do you notice about this? H plus OH minus yields H2O, or water. So basically I made water. Strong acid plus strong base makes water. Yep, it's always water. That's the answer to the original question. If you react a strong acid and a strong base, your net ionic equation is always that water equation that's right above my gigantic words. H plus OH minus yields HOH or H2O. So that's a really good little trick to have in the back pocket, because you don't even have to do the net ionic equation. If you're like, oh, that's a strong acid and that's a strong base, ta-da, the net ionic equation is that of water. So hopefully that's a little helpful thing for you. Okay, so this is a good place then to kind of just mention that what we've done previous to this is kind of the basic information. We've learned a little bit more about how to do net ionic equations with acids and bases. And the next little bit here is going to really be the calculation portion. So are you ready? Hopefully the answer is yes. Okay, so calculations for these acid-base neutralization reactions. So in your textbook, if you need to pause, go ahead and get it open to 159. And it's actually, the problem starts on page 158, but the majority of it is on 159. So on 158, it says, what volume of a 0.1 molar HCl solution is needed to neutralize 25.0 milliliters of a 0.350 molar sodium hydroxide? So this is a case of noticing the numbers that you have. Notice the values. Also notice that this is a neutralization reaction, right? Because they have sodium chloride and they have sodium hydroxide. I'm sorry, they have hydrochloric acid and sodium hydroxide. So this is an acid-base reaction, and they're asking you to determine a volume of acid. So notice that you're given two numbers for the base that you can actually use pretty much right off the bat. And by the way, just to sort of reiterate the question, here it is in yellow, maybe in a slightly less wordy fashion. Okay, so the molecular equation is always something that's important to make sure that you understand, because when you're doing neutralization reactions, you are going to need a little stoichiometry here. But what's awesome about this is that it's all 1 to 1 to 1 to 1 to 1. Everybody's 1 to 1 ratio, and that makes it super duper simple. So actually, as we begin this problem, this is where you have to start thinking like an AP chemistry student. Do we need to write down every last step? Yes, and at the same time, no. We can do a little bit of thinking in our head, and that will help us maybe write a little less down on paper. Okay, so we have our molecular equation. Again, we're reacting a strong acid and strong base, so we have our net ionic equation, which is just that of water. And now, again, noticing everything is a 1 to 1 ratio, meaning that whatever I react, that's what I'm going to create. And that's going to be really helpful. So first things first, you notice that the two values that you were given that go along with sodium hydroxide can be used together to cancel out liters. So you can see my math there. When I cancel out my liters, when I cancel out my liters, I get that I have actually reacted 0.00875 moles of sodium hydroxide. Okay, cool. So that's how much sodium hydroxide I reacted. Okay, well, if this is all a 1 to 1 ratio, if I reacted 0.00875 moles of sodium hydroxide, that means I also reacted 0.00875 moles of hydrochloric acid, right? 1 to 1 ratio. So now I use that molar amount with the molarity that they gave me in the problem. Notice I kind of flip it upside down. I have my moles that I start with, and then I have my molarity here, just kind of upside down a little bit, and the moles will cancel, producing a liter amount, which I then just converted into milliliters because that was what the sodium hydroxide was listed in, and that would be my final answer. So you recognize basically all you're doing is one stoichiometry problem, but you're using molarities with it. So again, we got to understand that big capital M means moles per liter, always separate it, and here you go. Okay, so record your questions. We can talk about those later. Moving on, there is another example. If you would flip the page to page 160, there is sample exercise 4.13, and this one's a little bit wordier, isn't it? It says, in a certain experiment, 28 milliliters of 0.250 molar nitric acid and 53.0 milliliters of 0.320 molar potassium hydroxide are mixed. Calculate the amount of water formed in the resulting reaction. What is the concentration of H plus or OH minus ions in excess after the reaction goes to completion? So if you remember anything from general chem, this reaction or this question reads like a limiting reagent problem, because they give you that final question at the end asking you about excess left over, and that was something that was really quintessential to limiting reagent problems. So we're actually going to start the calculation off in kind of a different yet similar way, I guess. And by the way, if you take a look at the way that I've rewritten the question, maybe it's a little bit more helpful to see, the numbers like this. So if it's helpful. Okay, so my net ionic equation, again, I'm dealing with a strong acid and a strong base. So my net ionic equation is that of water, which is all 1 to 1 ratios. So if that's the case, then that's going to be super duper helpful. Okay, so first thing I'm going to do, I need to take my my liter amount, in fact, it was a milliliter amount that I converted to liters for my nitric acid, and my molarity for the nitric acid to figure out how many moles of nitric acid I was using. Okay, makes sense? Okay, and then I'm going to do the exact same thing with the potassium hydroxide, because the fact of the matter is, at this point, I don't know which one of these is the limiting reagent, right? Remember, that was the deal with limiting reagent, is that you would get two numbers of two reactants, and you didn't know which one really mattered. So I'm going to have to do the calculation for both of these chemicals. And based on what I get for these answers, 0.007 moles of the nitric acid and 0.017 moles of the potassium hydroxide, which one is limiting? Hopefully you said it was the first one. The nitric acid is limiting because I have less of that. Okay, so When you take a look at this, again, you'll notice the net ionic equation deals with ions, whereas the equation that we have, the calculations that we have here are dealing with the full chemical, the nitric acid, the potassium hydroxide. But because everything's a 1-to-1 molar ratio, as I say in my next bullet point, the moles of H plus and the moles of OH negative are exactly the same as these above amounts because of the 1-to-1 ratio. So that's my limiting reagent. And so think about this, just read it with me. Also, using 1-to-1 ratios, if 0.007 moles of H plus react, and again, all will be used because it's the limiting reagent, then 0.00700 moles of water will be formed. And the reason why that part is in yellow is because that was one of the questions right here. How much water is formed? Same amount of acid that I would use up, being it's my limiting reagent. So that's the first part. The second part then, they ask about the excess. So what is the final concentration of the excess? Well, which one's the excess again? The hydroxide. Okay, so if this is the amount of hydroxide, this is the amount of hydroxide that I could have used up, but I didn't because this one ran out first, right? So if I'm going to use up, if I'm going to use up this amount of the acid, I would use up the exact same amount of the base as I use it. So this is my starting amount. The 0.017 was my starting amount. That's how much total of the hydroxide I had. I would use up the same amount as the acid, and then when I subtract those, I get the amount left. Okay, when I take that amount left and then divide it by the total volume. Notice that I had to do an addition here because I took 28 milliliters of the nitric acid and 53 milliliters of the potassium hydroxide. So I had to add the two volumes together to get my final concentration, or again, molarity, and I find 0.123 moles of hydroxide would be left over. Okay, so this is a pretty tricky one. If you need to at this point, definitely pause it. Definitely take some time to look this over carefully. The book factors it in a slightly different way. If it would maybe be helpful to you to look at the way the book presents it, totally up to you. Okay? All right. So moving on, we're going to talk about titrations real quick. Titrations are when you deliver an acid or a base into an acid or a base. It would have to be the other one in order to neutralize it. And it would be set up with something that looks like this. And so everybody should be familiar with this setup. The use of a burette. There's a valve at the bottom, which is actually called a stopcock, which is like the funniest word ever. And then you have a flask or a beaker at the bottom that contains your acid or base. It's important that you know the difference between the words titrant and analyte. The titrant is the thing that you are adding, and it would be in the burette, whereas the analyte is what you're analyzing, and it's in the beaker or the flask there at the bottom. We're doing a titration to basically determine concentration of whatever is the analyte. And so we have some sort of an indicator, and that would be in the analyte beaker or flask, and we would wait until it turned colors, and that would be then the end point, and we'd be great. And FYI, if you're still in your textbook, page 162 will show you a picture of the use of phenolphthalein, which you guys should be familiar with, how it starts off clear and colorless in acid, and then it will turn a bright pink, like 80s hot pink, when a base is added to it. So that's the basis of setting up a titration. So the way that they're going to, have you answer some questions about this are going to be with, of course, math problems. So here we have on page 162 also a sample exercise asking you to determine the neutralization and all this information with a titration. Now, please do me a favor. I want you to read the whole question. Sample exercise 4.14 on page 162. Read that whole question. Pause the video, please. Okay, so now you've read the whole entire question, and holy cow, that is a crap ton of information. What's good about this is you actually don't have a ton of work to do. In fact, if you're able to pick out the bits and pieces that you need, you're going to have it in no time at all. So for instance, do you notice that they gave you a gram amount of KHP, and they also told you the molar mass of KHP? Okay, well, when in grams, always convert to moles, and that would give you the moles of your KHP. And by the way, that's important because they want to know how much sodium hydroxide is required to react with that amount of the KHP. So you need to know the molar amount. Okay, well, in this, notice everything that they're doing here. It's all 1-to-1 ratios again. So if I need to react 0.00637 moles of KHP, that's how much of the hydrogen ion I would have. And if that's how much hydrogen ion I have, then that's how much hydroxide I have. So it's just all these 1-to-1 ratios. And if you can kind of take the maze through it all, it ends up being pretty darn simple. So again, if I recognize that my molar amount of KHP to react is the same as the molar amount of the hydroxide needed, and I now have a milliliter amount that it was given also, 41.20 milliliters converted to liters, that gives me a molarity of hydroxide, and that's the molarity of hydroxide I would need. So it's a crazy long problem, but in the end, it's kind of super simple. So just so you know, necessarily the length of the problem has nothing to do with the difficulty level of the problem. So look it over a couple more times, check it out. Okay, final thing, and I'm going to actually ask you to try this one in its entirety if you can. You may also notice that there's a solution in the textbook. Try it. Look at the solution in the textbook, and then come back to the video, and I will actually show you what I have here in my own mathematical way, okay? So pause a second, give it a try, see if you can work your way through it. It's a little different. I want a mass percent. Ooh, what the heck? Oh my gosh, you can do it. Give it a try. Okay, so maybe you did it, maybe you didn't. Do me a favor. Just try this. Check it out. Take a look at what I've done here. Recognize that really the only change is that last bullet point, because really the middle 3 bullet points are all 1-to-1 ratios, hydroxides and hydrogens, using a little gram amount there. But the last part is asking for the mass percent. So once I determine that I have 0.200 grams of this HC7H5O2, and I know how much was in the actual starting amount, you divide the two numbers, multiply by 100, and you've got your percent. So take some time to look it over. If you want me to go over it in more depth and detail later, I can. But these are just examples of how you can take acid-base reactions, neutralizations, titrations, and kind of throw it all into math. So that is it, ladies and gents. See you